Hi everyone, let's take a look at the following example. For the function f in terms of x and y equal to x to the power of 6 plus x to the power of 5 times y to the power of 4 minus y to the power of 3. Find fx, fy, fxx, fxy, fyx, fyy, fxxx, fxxy, fxyx, fxyy, fyxx, fyxy, fyyx, and fyy. What do you notice? So step one, let's explain what these notations really mean. And if we begin with the end in mind and reverse engineer, we're going to draw a tree diagram. Here's the first case. When you look at a function, and in this case, the function is expressed in terms of x and y, you can either solve for fx or fy. And fx means the first partial derivative with respect to x. Fy means the first partial derivative with respect to y. If you continue with the first case, fx becomes fxx or fxy. And let's highlight this. You can see exactly the meaning behind each case. So if you go back to fxx, that is the second partial derivative. And the way you think about this is first, you found fx, which is the first partial derivative with respect to x. Then you took that expression and you took the derivative with respect to x, which gives you fxx. So if you want to be very clear about this first x is this first x. The second x means you took f of x and you took the derivative with respect to x. And again, I will go through the actual example in a moment. Now, if I continue with the branch at the bottom, same idea. Fy could become fyx or fyy. So again, this means you can take the derivative with respect to x of fy. And again, if you think about fyx as a whole, that is the second partial derivative. If you follow this pattern, of course, we took the first partial derivative, then we took the second partial derivative, which means this next step is going to be the third partial derivative. So this becomes f x, x, x. Now again, if I follow this idea, fxx, this means fxxx, I take the derivative of fxx with respect to x. Now, same idea, you could have also taken fxxy, and likewise, the same thing. Now, the next branch, fxyx, fxyy, and of course, this is going to be fyxx, fyxy, fyyx, and fyyy. Let's just draw this a little bit better for you to make sure you can see this. Now, by inspection, you might look at this and say, I don't get it. Why there's so many cases? Is there any correlation we can make? And again, I haven't gone through the example with you yet. I am simply beginning with the end in mind, and I'm trying to tell you a couple of things in terms of the correlation. So there are three things I would like to share with you, or three ideas I would like to share with you. Idea number one, the following groups are the same. Now, here's the first group. If I think about fxy and fyx, these are the same, and I'm going to color code them. So fxy and fyx are the same. So this means if I took the derivative with respect to y of f of x, or I took the derivative of x from f of y, the final answer is the same. And again, we'll demonstrate this in a moment. Now in a different color. Again, I'm telling you f of xyy equals to f of yxy, which equals to f of yx. So again, if I look at this from the tree diagram, I'm looking at x, y, f, y, xy, and fyx. These are the same. Now, what do you notice? In the first case, xy and yx is the same, but just in a different sequence. Just like in this case, xyy, yxy, yyx, they're the same, but just in a different sequence. So again, press pause for a moment. You find the other combination. And when you press play again, I'll be here. Welcome back. So in a different color, let's do this in yellow. F of xxy equals to f of xyx, which equals to f of yxx. Again, fxxy, fxyx, fyxx, they are the same. So again, notice how the sequence is different, but the outcome is the same. So again, all I did so far is I gave you kind of the executive summary, and now I'm going to justify this with the actual example. Let's go back to the original color. Here we go. Now, the question is f of xy, which equals to x to the power of 6 plus x to the power of 5 times y to the power of 4 minus y to the power of 3. Let's start with fx. Again, fx means I take the first partial derivative with respect to x. So everything else are constants. So this is going to be a constant. This is going to be a constant. So this means fx equals to 6 x to the 5. Again, I'm using the power rule to find the derivative of x to the power of 6 plus, when I take the derivative of x to the power of 5, that's going to be 5 x to the power of 4 times this constant y to the 4. And of course, when you take the derivative of a constant, which is negative y cubed, that's going to be 0. So I'm going to leave it blank. Let's put a box around that. Let's keep going. Fy. So again, this means I'm taking the first partial derivative with respect to y. So in this case, x to the power of 6, x to the power of 5 are constants. I go back. Again, when I take the derivative of a constant, that's going to be 0. When I differentiate y to the 4, that's going to be 4y cubed. And I'm copying the constant x to the power of 5 right there. Minus, again, when I take the derivative of y cubed, it's going to be 3y squared. Let's keep going. fxx. Again, this means I look at this first case and I take the derivative with respect to x. So one more time, just in case, right? No one's left behind here. fxx means I take f of x. I take this entire expression and I take the derivative with respect to x. So in this case, when I take the derivative of 4x to the power of 5, that's going to be 20x to the 4. So 20x to the 4 times y to the power of 3. And of course, when I take the derivative of negative 3y squared, that's a constant, that's going to be 0. Now, what do you notice? This is the same as this, which means fyx equals to fxy, which we talked about from the beginning. So again, it's not a surprise, right? I'm going to put a check mark to verify one of the 3 ideas that we have talked about so far. fyy. Again, I'm going to take the partial derivative with respect to y, starting with fy. So I'm going to go back to this again, one more time, fy, and I'm going to take the derivative with respect to y. So again, in this case, 4x to the power of 5 is going to be a constant. So when I take the derivative of y to the power of 3, that's going to be 3y squared. Again, 3 times 4x to the 5 is going to be 12x to the 5 times y to the power of 2. And of course, when I take the derivative of negative 3y squared, that's going to be negative 6y. Let's put a box around this as well. So again, we're almost halfway. Now we're going to move on to the third partial derivative. Now I'm going to use a different color so you can see all the ones I'm doing now are the third partial derivative, and I'm going to continue with the following. f x x x. Again, this means I start with f(x(x) and I take the derivative with respect to x. So in this case, y to the power 4 is going to be a constant. Let's zoom in for you. So when I take the derivative of 30 x to the 4, that's going to be 120 x to the power of 3 plus, when I differentiate 20 x to the 3, that's going to be 60 60 x squared times y to the power 4. Let's put a box around it, just like that. Now, here comes the first of the three cases with the same answer. So I'm going to move on to f x x y. Again, this means I go back and I'm starting with f x x and I take the derivative with respect to y. So again, because 30 x to the 4 is going to be a constant, the derivative is going to be a 0. And now, when I take the derivative of y to the power 4, that's going to be 4y cubed. And again, 4 times 20x cubed equals to 80 x cubed times y cubed. And again, this will equal to two other parts in a moment. The moment is here. I'm moving on to f x y x. Again, this means I'm taking the derivative of f x y with respect to x. So again, y to the power 3 is going to be a constant. When I take the derivative of 20x to the power 4, that's going to be 80 times x to the power 3, and you copy the constant just like that. And again, it should not be a surprise that this equals to f(x(x)y. And I'm going to put an equal sign here when I come back to this in a moment. So here's the next part. I'm going to purposely skip f(x)y for now. I'm going to move on to f(y)(x)(x). Now the prediction is this should be the same as the other two. Let's find out if that is true. So I go back to f(y)(x) right here, f(y)(x), and I take the derivative with respect to x. Again, this means y to the power of 3 is going to be a constant. When I take the derivative of 20x to the 4, that's going to be 80 x cubed. I copy the constant. And again, it should not be a surprise that the fact that this equals to f(x)(xy), or I'm just going to kind of rewrite this here so you can see the correlation, f(x)(y)(x). Again, I'll put a box around this. So one more time, I am saying we have confirmed with this one specific example that f(x)(xy) equals to f(y)(x)(x), which equals to f(x)(y)(x). So at this moment, I would like you to keep going. Find f(x)(y)(y). And if you're doing this right, you would discover this equals to f what and f what. When you press play again, I'll be here and we're going to finish strong. Welcome back, everybody. So to find f(x)(y), I start with f(xy). So again, I'm starting with f(xy) and I'm taking the derivative with respect to y. Now again, since I'm going to take the derivative with respect to y, that means x to the power 4 is going to be a constant. So when I differentiate y to the power 3, that's going to be 3y squared. I put y squared right there. 3 times 20x to the 4 is going to give 60 x to the power 4. And again, I'm telling you in a moment, this equals to f of something and f of something else. And I hope you can tell by the pattern that f xyy equals to fyxy. Now again, let me go back and really show this. I can't conclude this so early. Let's go back to fyxy. Now again, what does this really mean? I go back. I find fyx. Now fyx, by the way, is right here. That's 20x to the 4 times y to the power of 3. And I'm taking the partial derivative with respect to y. So again, when I differentiate y to the power of 3, that's going to be 3y squared. The 3 multiply with 20x to the 4 is going to give 60x to the 4. So this is the reason why these are the same. And of course, let's write this better for you. I can put a box around this. And again, fxyy equals to fyxy, which equals to fyyx. fyyx equals to, I go back to fyy. Again, we did this from the top. And I'm going to take the partial derivative with respect to x. This means y is going to be a constant in this case. So you can tell that this negative 6y, when I differentiate in a moment, that's going to become 0. Now, when I take the derivative of 12x to the power of 5, that's going to be 60x to the 4. So I write down 60x to the 4, and I copy y to the power of 2. And again, this equals to, as expected, fyxy, fxyy, which equals to fyyx. And again, I'm going to put this back here so you can see it together. So, just like that. One more part, fyy. So I go back to fyy. Again, what I'm doing is I'm taking fyy, and I'm taking the partial derivative with respect to y. So x is going to be a constant in this case. So in this case, when I take the derivative of y squared, that's going to be 2y. So I'm going to put a y right there. 2 times 12 x to the power of 5 is going to give 24 x to the power of 5 times y. And of course, when I take the derivative of 6y, that's going to be 6, just like that. I hope this makes sense.